wrote a lot. There's not many people in here, but it's the longest grading session. And in a class like this, I just don't take off that much. Like, if you don't do it, that's the big problem. But like I usually, and I just take off like a point to be like, look here, it's not punitive. None of this is, it's not meant to be punitive. Cool. Well, if anybody wants to join in on just a little centering practice before we start, let's just do that. Because Anna's got a split soon, and I don't fill up the only time she has here with not real analysis. Just take a minute to check in with your body. Maybe the only time today you'll do this. So it's really important. Just turning our attention away from our thoughts and doing things. Can you just sit for 1 minute and literally veg? Just let go for 1 minute. Give yourself this present. Find yourself doing something, just let go. Just drop the ball. Just bring yourself back. Definitely good to hit the reset button every day. Any questions, my friends? Anything you want to talk about? I think we have homework 3. Is that Wednesday? Is that the due date on that?
Friday.
Was it Friday? Okay, that sounds good. And if that was too soon, I was going to say let's move it back. Friday? That sounds great. So Wednesday we'll talk about it. Okay. All right. That sounds good. Cool. So today we're kind of embarking on our real journey. Everything else has been getting some tools and basic ideas ready. And now we're going to move forward and really get into analysis. And we're going to start off today with 2.1. Oh, excuse me, 2.2. So my request of you is to read 2.1 on your own. This is on rearrangements of series. So when you have some infinite sum. And it's probably something you've never thought about before. And it's really interesting. Maybe in Calc 2, your instructor went and touched upon rearranging the terms in an infinite sum, but probably not to the depth that section 2.1 goes into it. And it's just kind of a breezy, as breezy as this book could get, chatty discussion of why do we even care about sequences. So right off the bat, this is a series, right? And a series is a sum, generally of infinite. We usually assume infinitely many terms are possible. It is made up of a sequence of terms. So these are the terms, and they form a sequence. And so a sequence can be written like this. And this is just literally an ordered list of real numbers that goes on forever. So this is notation here. I'll put a bunch of ors here. All of these are completely okay. You might want to put the indices on there. But what this means is this. And sometimes you'll actually see it written like this as well. And I will probably slip into this notation. These all mean the same thing in our class. A list of numbers. So when you do Calc 2, the first time you see this stuff, I think is in Calc 2 probably, maybe earlier on you talked about geometric sequences, if you had like a really rich mathematical background. But we're gonna pull back and take a higher level view of this. And this is a really interesting way that I throw out to my Calc 2 classes for better or worse. I don't know if they get it, I don't know if it helps them, but I think it'll help you, and I think it'll provide a different perspective. So I'm going to give you a weird definition. A sequence is a function. So instead of it's a list of numbers, it's a function. So F that goes from the naturals. The key thing is that the domain is the natural numbers. That's what makes it a sequence. Domain equals naturals. Or maybe we toss in 0. And there'll be times when maybe Z or something like that, but mostly this is it. And you can picture it like this. Well, let's tie it back to this previous notation. So we can say, given a sequence like this, I could rewrite that as a sub n is just a function of n. And there's some formula here that gives me this sequence. So given a sequence, we have an associated function. This is all pretty up in the air right now, kind of floating around. So let me make it solid with an example. And the one thing, I never have mentioned this up front before, but I wanted to now because there's a consistent confusing of the term sequence and series by folks in this class, or my experience teaching it. So I just want to point that out up front, that a sequence is not a series and vice versa. So when you see this, I'm not thinking of this. This is a series. We'll get into that soon enough. That's a P series. P equals 2, it converges. I don't know if any of that is like we're waking up ancient beasts from the past. But we're definitely going to summon those things into full reality very shortly. But I have the sequence here, and so I could write that out. And this right here, this would be f of n that I'm referring to. We could write this as 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, etc. And I can also plot these. And I've mentioned this already. I think I mentioned this last week when we met at some point. But you can plot it like a normal function, and this is a very helpful thing to do. So for example, this sequence here looks like 1 is my first term, so this is 1, 2, 3. And then we go to a quarter, so let's see what does that have? 1/4, and then 1/9, and that's like a little less than half of this, and so on and so forth. But I highly recommend, when you can, making a little sketch of the sequence when things start getting weird, and there's going to be some weird problems, which shouldn't surprise you by now, right? There's going to be stuff where it's like, what? I don't know. It never hurts to start drawing things out. So let's take a look at another sequence. Let me give you a couple more examples so we have things to toss about. So let's call this example 1. And I hadn't planned on going this route, but here we go. Here's example 2. A sub n is -1 to the n. What does that sequence look like? What is that sequence doing? Grab some tea. Yeah, Kayla's making some, she's miming the answer. Yeah, back and forth. So you just start plugging in, and literally, I would crank out a few terms of any sequence I originally had until I saw the pattern, and here we see the pattern real quick. Right, just gonna alternate between 1 and -1. Let's draw a picture as well. So here's n, here's a sub n, 1, -1, 2, 6. What could you do? So this sequence starts out at -1. What if I wanted a sequence that did this, but it started at +1 and then alternated? What could we do?
N plus 1.
Say that again?
So like -1 to the n plus 1.
Yeah, bump up the exponent by 1, right? So if I did this, then it would start on an even power. So I could set up the cadence in any way I want. Just wanted to note that. What about, let me ask you this, could you come up with a sequence? Can you come up with a formula for a sequence that does this? How would you do that? Let's just say you don't have to reinvent the wheel. Being able to build sequences that do things is going to be kind of an important skill. I think I've got the recording problem fixed, Anna. So we will actually have a good recording from today. I cleared out everything on my iPad.
That was a space issue?
Yeah, because I kept deleting stuff, but no space was showing up, and I realized there was like this trash bin. Yeah, I know, right? Oh, God. And I just deleted everything that was on there. And if I don't know about something that was good on there, well, this sequence got, yeah, those aren't great lined up. Anybody, can you help me out here? Diana, you got anything for this one? What are you thinking?
Straight line.
When you say straight line, can you explain what you mean a little bit?
We're still doing -1.
Oh, no, we're doing this guy here.
Okay.
Do you see how we could move from this sequence to that sequence? And maybe try to think visually. What could we do with these points to end up with those points?
Would you do -2 instead of negative? No.
I mean, that could, there's definitely other ways to do it besides what I'm suggesting. So, okay, you want?
-1 to the n plus 1. Like
Yeah, we
plus
could.
one
So we
outside
could
of
add
it.
1
Yeah.
to this thing. We could. So, in other words, this sequence here, we take the -1 to the n, and then we add on a 1. So it's not too fancy. It's like, what I was picturing is taking this whole thing and just shifting it up 1 unit so that the -1 goes to 0 and the 1s go to 2. And this accomplishes that. Are there other ways? I can think of at least one other way. And it has to, and Diana's thing kind of tipped me off on it. What about this? No, that's the same damn thing, wait. Maybe I don't have another way, because this is kind of this is the straight line that Diana was thinking about, right? It's like this guy here, bouncing around that. It doesn't matter. It doesn't matter. I thought I had something, but I was so wrong. All good. I wish I could come up with one because these things aren't necessarily unique, but you know, it is what it is. How about this? Could you come up with one that does? How about that one? And we'll call that example 3. This is just some kind of limbo thing here. Think you got something, Anna?
Trying to figure out if that's correct.
Let me take a look. Yeah, I like that. I like that. So could you mind if I share that?
Yeah.
Anna's got this one. I like it. Works for me. Because we've got, so Kayla, I see your head like turning to the side. Maybe I'm misinterpreting that. So let's check it out. So -1 squared 1. So 2 is going to be -1/2. Oh, yeah. Not. How do we fix this? It
That's
isn't.
why I was trying to figure it out.
Yeah. How do we fix this? Because the bottom's going to get affected by the exponent, right? So that's not quite. It's so close. How do we fix it?
Pull the -1 out.
Pull the -1 out and take this off of the end as well, right? So, actually, so not quite close, but what we want is a sub n, and we'll just put the -1 to the n plus 1 on top like that. And now we got it. Does that sound right? Anna, does that sound good to you?
Yeah, I was trying to figure out because like something isn't right.
Yeah, and I looked at it and I totally thought it was right. And then Kayla started cocking her head. So we all agree that looks good. That one. It's got the alternation. So anytime you want alternation, a plus minus thing, this -1 to some power is going to be your friend. So this is for any sort of alternation or oscillating. Oscillation. Just like with the 0-2 thing, that's an oscillation. Doesn't alternate sign, but remember it did involve that -1 to the end. So when you see stuff bouncing, I would include this for sure. Okay, so let's think about the sequences we've been given. What was the first sequence we had? What was example 1? A 1 over n squared? Yeah, so we had 1 over n squared. And then this sequence here, let me actually draw it out real quick, because I didn't do that. So we go 1, and then we go negative a half, and then negative a half, positive a third. And what we see is oscillation with like a dampening effect, kind of like a pendulum dying out, or a spring losing energy, or something like that. So that first one was this, and you've already got it, I'm just kind of getting it. I think this is something like that. So notice that this first one is settling down. The values, as n gets bigger and bigger, this thing is getting closer and closer to what? 0, yeah, right? Because you're 1 over a bigger and bigger number. So this approaches 0 as n approaches infinity. The old calculus idea of the limit. This one here, similar thing. It's not as clear cut because of this oscillation, but you can see that eventually this dies out and heads to 0 in a different way than that one. So here as well, a sub n converges to 0 as n goes to infinity. But this one here, not so good, right? This never settles down. If you were to claim, oh, it eventually all settles down to 1, I would say no, because at any point you pick beyond that, there's always another negative 1 kicking along. So this thing here, and we're going to formalize this all in a minute, but this doesn't settle down. As n goes to infinity, and we say it diverges. So this is all intuitive. Now we don't do anything purely intuitive in here, right? That's for Calc 1 or 2. And here we get hardcore, and we get a definition out. What does it mean to converge? So that's what today is about quite a bit. So definition. Given a sequence, a sub n, we say a sub n converges. We'll write it out in a couple ways to, let's just call it capital L for the limit. A sub n converges to L, i.e. a sub n converges to L, i.e. we're going to put a bunch of different notations up here. Limit of a sub n equals L. All those things are good. Notice this has an implied n going to infinity underneath it. So this has an implied n going to infinity. We're getting more sophisticated. Right? These 400 level math classes, we know, we can assume that the reader knows the context and then can grok what is being written here in the appropriate way. So we would say this if, let's write this out, for every positive epsilon, you're going to get good at doing epsilons this semester. This is our first one. Oh no, we had the first one. We've already had one. That's right, we already had one, and we're going to see that one again today too. But for every epsilon greater than 0, we can find a capital N, which is a natural number, such that a sub n, the distance between a sub n and L is less than this given tolerance epsilon when n is bigger than or equal to n. And let's draw a picture, because there's a nice picture that goes with this as well. So here's n, here's a sub n, and then let's say that this is L right here, that value, whatever that real number L is. And the a sub n's, let's say, maybe they go like this. They'll kind of do that little oscillating deal, but settling down. So you want to draw something like that. Pendulum settling down to equilibrium kind of deal. You give me an epsilon. So if this is L plus epsilon right here, and this is L minus epsilon, there's a little tube that's formed here. That tube, that tube is a cheaty tube. Oh my God, it's so bad. So I've got this little tube right here, and then there's a center line, and it's epsilon in each direction, with L in the center. So you tell me how wide you want that tube to be, and I can find a spot in the sequence where from there, so like right here, here's the N we're thinking about right here. There's our capital N because that's the first element of the sequence that fell into the given tube. And so from here on out, everything else is inside the tube. Again, I call those epsilon tubes, and I'll say that. Somewhere I learned that a long time ago, but they make sense with this little picture. And they translate really nicely into higher dimensions as well. It's a tube when it's written like this. It's a neighborhood when we're just kind of writing it on the real line, but we'll get there. So, one other way to say this, let's rewrite this one more way. So, i.e., let's get fancy. For all epsilon greater than 0, there exists a capital N that is a natural, such that little n bigger than or equal to big N, or little n greater than or equal to big N implies a sub n minus L is less than epsilon. This condition here, so this is the super fancy compact definition of convergence. That's the one you show your friends to impress them with your mathiness and say, oh, yeah, here's what we do in math classes. And it looks like it is a foreign language, right? So this little thing right here, notice that this just means the following. You want to be able to convert that type of thing into a double inequality. It's saying that this thing is no more than epsilon units away from 0. So this is another way to say that. And here it also says this. These are all the same thing. And there's different times when each one of those ways of looking at that inequality are going to pay off. This one right here really pays off when I'm looking at this picture here. It syncs up with the epsilon tube thing, that the a sub n's fall into that little epsilon tube. Any questions on this, friends? Is this sounding okay? So let's talk about how to work with this definition. How to use this definition to prove limit a sub n equals L in a particular circumstance. And your book has our book, my book too, has a really nice outline of this. Let me point you toward it. On page 45, there's a nice template. I'm going to kind of do this basically the same thing, but here I would say see page 45 template for the proof, and I'm going to go through it again. But when you see it the second time, it'll be really, your brain will be ripe for it, for sure. So then I will proceed by example. Show, and let's go to our old friend, example 1 equals 0. So think about what we need to show. I'm going to do some scratch work, and I'm going to encourage you to do scratch work. And then put it back together in reverse. This is how you do fancy math. You do it in kind of the backwards way, and then you present it the forwards way, and it looks mystical. So here's the scratch work that you'll always want to do to get your beautiful proof. So we know we want this to happen. We know we're going to need that to happen. So what we're going to do is we're going to set that up. So here, that is, what would that be? 1 over n squared minus 0 less than epsilon. Literally just plugging in all the stuff from the problem. And then solve what n, at what point does this become true? So literally solve the inequality now. And solve the resulting inequality. So the goal here is that we're going to have epsilon is, n is going to be a function of epsilon. So that n is a function of epsilon. And so let's take this out. So you can get rid of, the good news is, remembering that n is a natural number, I can get rid of the absolute values here, because that's 0, and I have this. So solving that, you flip both sides, changes the inequality. So n has to be greater than 1 over square root of epsilon, which totally exists because epsilon is positive. So that's cool. And I want the positive square root because n is going to be a positive number. So I picked the positive square root here for that. Okay, so as long as little n is bigger than this 1 over square root of epsilon, this holds true. So you gotta think, if this holds true, then this holds true. So this tells us how to pick capital N. We're gonna pick capital N to be bigger than 1 over square root of epsilon, and then when little n is bigger than that, we've got our condition. So let me write that out now. So that's the scratch word, proof. Let epsilon be greater than 0. And choose capital N to be a natural number greater than 1 over square root of epsilon. Oop, that's a 3. And we can always do that. Why? Why can I always do that? Some ancient Greek. It's not Pythagoras. Do I really have to keep doing this? Okay. Who do we summon from the Greek world? Just start guessing some freaking Greeks. Who? Yeah, Archimedes. I see him coming through the smoke. His face is manifesting. So, because of the Archimedean principle, we can always find a natural number bigger than any given real number. Thanks, Archimedes. Is Archimedes with an eye like that? I don't know either. It looks kind of weird, but who gives a shit? It doesn't matter. Yeah, there you go. Yeah.
What's he gonna do?
And his spirit cannot harm us. It's incorporeal. So, all right. So choose this. Then, if little n is bigger than or equal to that cut point, we have 1 over n squared minus 0. So now I wouldn't put this, this is a little note for us to see this the first time. This is just the a sub n minus L right here. Because now I'm going to show that that thing will be less than that epsilon given what I've just set up, which is equal to 1 over n squared because n, well, because this is just 1 over n squared. I don't think we need to explain that. And if it needs explaining, let's talk. And so then this is going to be less than 1 over hold on, let me get my head straight here. This is going to be less than, oh, like that? Yeah. I'm just trying to make it a little clear path to where we're going. Does that make sense, Trinity? Your head, I saw your head like cock a little to the side. This is a lot of that going on today. So that's equal to that because of that. And then this, if you take this inequality right here, this is less than 1 over 1 over, oh bless you, square root of epsilon squared. Because n is bigger than or equal to this thing. And then this, you just simplify this out, and that is literally just epsilon. The key is to put enough steps in there so that your reader can understand how you got this to be truly less than epsilon. And you're going to get good working with inequalities. Remember, when you flip an inequality, it flips, when you flip both sides, it flips the inequalities order. So we have this when, oh, we already got it. And we're done. Thus, we've satisfied the definition of limit, which says, right, where is it at? I guess I had it up there at some point. It was there before, the way I wrote it with this implication. Thus, 1 over n squared converges to 0. Oh, good, we got lots of time. Can I answer any questions on that? Because I want to do some practice with this, so that you can actually write one of these before you leave here today. All right, let's start off chill. Let's do this one. Show so this was example 3. Let's prove that. Give it a shot. I'm going to run to the restroom. As usual, throw it out the thing and run. kind of the leap I think you need to take. At least that's the leap I need to take in my mind, because that -1 to the n is a mess. And if you're trying to work with that, getting rid of it is so much better. Does everybody feel comfortable that these two statements are equivalent? Because I'm applying that absolute value to the top. So here, let me go a little slower, because I'm not sure you do believe me. So certainly the 0 is just vapor. This is this. Yeah. And then the absolute value of -1 is just, or +1. Either shit. Right. that's that. So it's always 1 on top. So this is literally this thing right here. Yeah, does this sound good? And then we solve for the n. So n has to be greater than 1/epsilon. That's your mysterious work. That's your big move right there. So this gives you the cutoff from which this happens. So the one thing to keep out is that this n is going to be a function of epsilon. This is the call and response. This is the call. How close? Show me I can get this close. This is the response. Okay, go out that far. So this is the game. No matter what, you want to set it up so that no matter how close somebody wants to be to that limit, you've given them a formula and a way to get that close from some point evermore. Is that, so before we go on, is this making sense? Is this sound okay? Yeah, actually.
So is there a reason that one n is like greater than or equal to and this one's just greater than?
Oh, yeah, it should be, you're right, it should be greater. Yes, thank you, ma'am. Yep. There is, but it's because it's bad and wrong. Yeah. Yeah, because we want to clearly be away from that. Thank you. That was a good catch. And just then, you know, I don't know how much you want to clarify for your reader, but we just want to remind ourselves that, and again, Archimedes hooked us up with this. Is there any other questions or comments? Because that was a really good one. Okay, so this. Then, so you set that up, your mysterious inequality. Then we have, or whatever your language is, you know, don't use my language, use the language that feels right to you. Develop your own proof style. We have -1 to the n over n minus 0. And notice how I'm kind of almost going through the scratch work in some ways. It's kind of going to look like the scratch work. So this is equal to 1 over n. And then that, shit. Then if, how about this? I like to have this set up a little ahead of time. I like to have my reference to my little n right there. So if little n is bigger than or equal to that cutoff, we have, because then I can do this nice thing here, which I think is a helpful, for me this is helpful, this little link. And then this is going to be less than 1 over epsilon, which just is epsilon. And you've proven it. You're done. Literally, because now you tell me how close you want, I can tell you how far out you need to go to make this happen. And you might want to say thus, you know. I think I like summary statements at the end of a proof. Yeah. Let's see. We got good. Let's do one more. Let's push it up just a little bit. So I'm gonna give you something here. Double problem. consider the sequence. I don't know, add as many C's as you want. The sequence a sub n equals n over n plus 1. So question 1 is, does a sub n converge? If so, to what? Answer, it does. Because I'm going to ask this next question, which is, prove it. So to come up with a candidate limit, prove that you go to that limit. So just take a minute on that. Just think that through. And you might want to, to get a handle on that sequence, maybe write out some of the terms and see where you think it's headed. Questions, just let me know too. Sanity checks or anything. You're okay. Yeah.
Are we allowed to do this?
So how? It's kind of true.
Okay, that's what I thought.
But so I would like in this move. So I would make this move first, Kayla, because for me it definitely helps. Remember that when you have this, that's a double inequality. So.
Oh.
So I would rewrite it like that and then do the thing you're doing, because then you only got half of it. Okay?
Perfect. We can just, yeah. Thank you.
You're welcome. Can we, at least as a group, get a candidate for the limit? What do we think? Yeah? Fingers? Yeah? Okay, cool. Yay, all right, we're at 1, right? It's getting closer and closer to 1. It's a half, 2/3, 3/4, 4/5. I'll graph it out while you're all working on that part. I don't know how you get at it unless you make this computation first. And there might be other ways. That doesn't mean there isn't a way. In my mind, that definitely is an essential first step, and then you can just strip off the negative, and it kind of ends up a lot like the last problem. 1 over everything. I'm going to do something a little bit weirder. I'm just kind of curious, did everybody go this route?
Yeah.
That's totally cool if you did that. Let's catch up and talk together. So I think we all agreed on this. Is everybody okay with this flow right here? Make sure it's cool. Let's clarify anything that's unclear. Yeah, all right. So check it out. You can totally do this, and this is great. But notice that if this is true, if this, and it's a little cleaner, then this is it's also greater than this, because if you subtract off 1. So we could, if we wanted to be fancy, do this and then insert the -1 in a bit, and we'll be all good. So if this is true, then we come to our this, and we do our finagling, reminiscent of stuff that's come before. We literally just get to that. And then that is going to be, oh shit. I keep forgetting my setup, my injection here. Then if little n is bigger than or equal to big N, we have, or implies, or whatever, we have this is this, and then this has to be less than or equal to 1 over big N plus 1. And then this is going to be less than, and here's where my little trick is going to come in, 1 over, so this would be 1 over epsilon plus 1. Okay, yeah, we'll do that. But notice that this is smaller than this. Because this denominator is bigger here, right? If epsilon is positive. So now I've got that, and I wormed my way back to epsilon. And we prove it. There's no unique route right? So like, as long as you're doing legit math, your route might look different. As long as the steps are logically consistent, you're good to go. This is one way. Can we talk about that at all? Eventually you'll have some of these to do. You've got enough to do right now. I'm sure on Wednesday there'll be some more appearing. The underworld of math. All right. I want to work on a problem together. Does anybody not have their book or a form of book with SC books? And I know yours is electronic. Actually, you got an electronic. Awesome. I wanted to play a fun game. I would like to look at some strange things. So first off would be exercise 221 on page 47. There's some great exercises in here where they tweak the definitions of limit, and it's a great chance to just expand our minds around that definition of limit and then quantification. So in exercise 221, it says, what happens if we reverse the order of the quantifiers in the limit definition? So the original definition is that for all epsilon greater than 0, there exists a capital N, which is a natural, such that if little n is bigger than a capital N, we have a sub n minus L less than epsilon. So that's the definition. They're saying, what happens if we flip the for all and the exist? So new def. And I think they call this, do they come up with a name for it? Vercongent. Yeah. So here we say a sub n verconges to L if there exists an epsilon greater than 0 such that, we got to put that in for ourselves, for all n natural, let's be clear about that then here. If little n is bigger than or equal to that capital N we have. So we're not writing like the contrapositive or the negation or anything like that. We're just writing this out. So the question is, what does it mean to be vercongent? So this is an exploratory thing at this point. Let's see. Give an example of a vercongent sequence. Is there an example of a vercongent sequence that is divergent in the classic sense of not converging? So I'll write these questions up. We can talk through them. So your first example is, can you come up with an example of a vercongent sequence? It might be a little painful at first to just pull apart that definition. Now, I would say before just coming in and trying to find the example, draw some diagrams. What does this mean? Might even help. Think about it like this. got something, Trent? You're still thinking, okay. It's quite an exercise. Looking for, you might not want to listen to this, but I'm going to give you some tips if you want them. Notice that we're saying we can find a single epsilon. That this is true basically for any little n. Look at this here. For all natural big N, if little n is bigger than or equal to big N, this might as well say for all little n that are natural. Because we could just let this be n equals 1, right? So for all n, this could be literally be this one. So this could be, little n just has to be a natural. Then this happens. What did this mean? So let's pull that apart the way Kayla was pulling that apart before. Right? And then that means this. Yes, ma'am. Yeah.
So it's like a bounding question.
Yes.
Okay.
Yeah.
So
Yeah.
is it like bounded the whole way through the series?
That's it. Exactly. Is the sequence bounded? So yeah, perfect. Did you have that before we even went here? Were you getting there?
Yeah. Because it's like when you drew it out, like the little cups, like if you, the epsilon tube, so basically just make the epsilon tube big enough that it fits everything?
That's right.
Okay.
That we can find, yeah, that there exists some epsilon tube so that whatever this number L is that we're claiming. So let's say over here, let's pick a sequence. Let's just make a weird one. So here's a sequence that does this. Notice how I don't have any values in it. Just doing some weird, okay, they get really close together out there, but that's okay. They're supposed to be regularly spaced. So there's my sequence. Collection of dots. Convergence to L. Well, it's kind of hard to pick L, but I'm going to tell you the way this works, you can let L be pretty much about anything. Here. So let's say that's L, right in the middle, took like the arithmetic mean or something, right? Like it did a linear regression on it, and then it's got a horizontal line because there's no correlation. And then, so it picked L. Does there exist an epsilon so that if I move epsilon units up and epsilon units down, everything's in there? And yeah, right? I got lots of epsilons, right? So here's an epsilon. And then say there's L minus epsilon. Everything falls inside there. So yeah, good job, Kayla, absolutely. This essentially says that the sequence is bounded. Because let's take a sequence that's not for conjugate. Sometimes it's almost always helpful to see an anti-example. So let's say I've got a sequence that goes like this. Say, maybe something like n squared or something like that with literally a parabola just going up. Here, this is not for conjugate because no matter what L I pick, there's no single epsilon that can encase everything between L plus epsilon and L minus epsilon. So assume this is unbounded. Do you see how I can't find any epsilon to contain them? There's no upper roof. There's no lower roof. Or see, floor. No lower roof below me. Unbounded. So an unbounded sequence is not Vercongent. Cool. Does everybody feel good about that? So you can give an example of a Vercongent sequence by just giving a bounded sequence. Any bounded sequence works. Clearly, there's an example of a Vercongent sequence that is divergent. How about good old -1 to the n? That's a happy one. Let L be 0, let epsilon be 2, joy, we're done. Check, they're all inside the, here's 2, here's -2, everything lives inside that little tube right there. So the Vercongent lets you pick the center of your tube and the width of your tube. How about this? Is the L unique in this definition? Is there only one L? So like for this sequence up here, is that the only L I could have used? Are you saying no, Ashley? You kind of look like you're saying no. That's the right answer. Yes, you are saying no. Why are you saying no? Because that's a great thing to say.
You could move it up slightly and then change your epsilon.
Perfect, yeah. I could have picked a different epsilon or a different L. Let's say I let my L be up here. And then just double epsilon, right? So now there's the L minus epsilon, because I get to pick that epsilon. So I get to pick the center and the width. So I would say here, actually, there are infinitely many L's once there is one. Yes. In fact, there are infinitely many L epsilon pairs that work once one pair works. So Vercongence does not result in a unique Vercongent limit, or whatever that thing is going to be called. But in the last couple minutes, I want to contrast that really quick. Regular convergence does actually provide a unique limit. So notice this L is not unique here, but give me one last minute. Prove this to you and show you a little trick along the way. I think I have time for this. But limits of convergent sequences in the classic sense, not Vercongence, are unique in contrast. So, proof. Suppose I've got a sequence A sub n, there I'm doing it now, is convergent. And that it has two different limits. So here is a fun little game we're going to play. Notice that absolute value of L minus M. Here's a good trick. You're going to use it a lot this semester. I'm going to add 0 in here in the cleverest of ways because I know where I want to head. I want to head to that limit definition, right, where there's stuff like that floating around. So I'm going to subtract off a sub n, add on a sub n, and you've probably seen that trick somewhere. You've taken enough math classes to see that happening. So check this out. What am I doing when I say this? How did I get that? What inequality? I've only got one. What famous inequality? Thanks. Rectangle inequality? No. Who? Thanks. Rhombus inequality? No. Thank you. Good. I was like, do I have to come up with another goofy one? Okay. Thanks, triangle inequality, because I've got this, and so it's less than or equal to the absolute value of those sums of things. You can clump that together, And given epsilon greater than 0, we can choose capital N such that a sub n minus L is less than, check this out, epsilon over 2 when little n is bigger than or equal to capital M. And so this is because of this. And we can choose, it's called capital M, such that a sub n minus m is less than epsilon over 2. This is another trick. Notice, I can make them less than anything I want. I'm picking something that's going to be really pretty when I add the two damn things together. I want to end up with an epsilon. And this is slick. So that is when n is bigger than or equal to capital M, because a sub m also theoretically converges to m. So if little n is bigger than or equal to the max of these two, both of these things are in effect. I just picked the bigger of those two, how far out we're going. We have L minus M less than or equal to, and now I'm going to rewrite this, a sub n minus L plus a sub n minus M. We can just switch them because it's an absolute value, less than epsilon over 2 plus epsilon over 2 equals epsilon when, oh, we already got it. What does that give me? And I'll let you go. Sorry, I'm keeping you late. I owe you time. So I've just shown that no matter what epsilon is, I can make this true. So what does that say about L and M? One of our very first things, it is, I hear sounds coming from out there.
Shouldn't the difference be 0?
Shouldn't it be what?
Like the difference of L and M be 0 because we're trying to
It is, yes. That was our, yes ma'am, that's what I'm trying to get to. So it was theorem 126. So by theorem 126, thanks for staying everybody, L has to equal M. We'll come back, we'll revisit all this on Wednesday. Looking forward to your questions on Wednesday. And we'll do more practice with sequences. And thanks everybody. 5 more classes till spring break.
Seriously?
That's your eyes. I was like, yeah. Yeah, I keep tabs on that stuff.
That's concerning.
It is quite concerning, isn't it?
I just hate how early our spring break is.
You what?
I hate how early our spring break is.
It's so stupid.
It's so dumb. It's
It's
earlier than everyone I know.
spring break.
I feel like
It's February.
Yeah,
It's
yeah.
February.
It's not even spring.
Not even close.
I I feel like if I really like skiing, it would
Oh,
be
thank
good
you.